Okay, so this is going to be the next video in a little series that I've been putting together talking about a hobby engine that I've been working on, trying to imagine what it would be like to write a tech engine, but knowing what we know now about both the kind of output that we want, PDFs and modern fonts and maybe HTML output and things like this, and also knowing what we know now about computer hardware in the modern era as opposed to what hardware was like in the 1980s. Right? And so what I really wanted to talk about was some of the things that I've learned about data-oriented design from reading the TeX's and how I imagined applying that to this engine rewrite that I've been working on to kind of get some performance benefits out of it. But I thought before I do that, maybe it would be good to have just like a little interlude where we talk a little bit about, well, what is TeX's fundamental representation of most of the memory that it needs to store, both information about the things that it's reading from files or how it stores information that's going to later use for typesetting or things like this. And so I thought I would talk a little bit about what that memory model is, and then show a little bit about the difference between kind of how it's implemented in existing engines and how I'm thinking about trying to kind of rewrite this and update it a little bit. Okay. So I don't want to be unkind. I think many of us have somewhat mixed feelings about Overleaf, but I want to say at least one nice thing about it. And if you've ever looked at the documentation center for Overleaf and you scroll all the way to the bottom, you'll see that there's this in-depth technical articles section hidden away. And some of these articles I think are really nice kind of beginning introductions that teach you about some of the internals of tech, some of the internals of LuaTeX for that matter. And I think some of them are really nice, really well written, and really helpful for understanding what's happening when you take a tech document and try to run it through one of these engines. So the first thing that I want to look at is actually just this article here, what is a tech token list? So the thing to keep in mind is that almost all of the information that tech uses and needs to know about during the scanning to typesetting process is stored in one huge monolithic array of memory. And one of the important parts of that huge array of memory is dedicated for these tokens, right? We'll hand wave a little bit for the experts in the audience. And so, if you've seen in computer science the idea of a linked list, I think this article will make a lot of sense to you. The idea here is that, Knuth wanted to be very memory efficient and memory efficient with how he was storing the information about kind of sequences of tokens. Tokens, for instance, are the representation that tech has of as it's reading a file, character by character, it translates that character into some internal token representation, which has information both about what the character is, what its semantic role is, and things like this. And it's stored in this huge array of memory as kind of one, we'll call them memory words, because that's what they were called, right? And half of the memory word is dedicated to holding look at this little thing, is dedicated to holding the information that's actually contained in the token. What is the character? What is the character code? Things like this. And the other piece of information, the other half of that chunk of memory, is dedicated to saying, where should you look for the next token in the list of tokens you need to know about? And so it's either basically a pointer in this big array to the next token, or it's a special flag that says, the list has ended here, right? And so there you go. I think this is a very nice kind of visual representation of how these linked lists work. And we're going to go a lot deeper, right? Because one of the things that's kind of interesting about this monolithic array of memory is that not only is tech storing these tokens in it, but is also storing these kind of different nodes, right? And so nodes are the kind of term for the way tech stores information about almost everything else. So tech has a notion of, this is going to be a piece of glue. A glue is going to have something that represents a space, either in a vertical list or a horizontal list. It can stretch or it can expand and things like this. It needs to know what element is after the glue. There's going to be things like boxes, things that hold information about inserting material, putting a float somewhere or something like that. Heuristically, it needs to have mechanisms to know about handling footnotes and kerns and potential hyphenation points and how much penalty to assign if you have to break a word at a hyphenation point and all this stuff. And one of the things that's important is that all of those different flavors of nodes need different total amounts of information to describe their contents. And so the question is, how do you generate a monolithic array of memory that can hold both tokens, each of which is just one memory word long. We'll see exactly what a memory word is in just a second, and some of which are variable in size, right? Something might take 2 memory words, or 7 memory words, or 9 memory words, or things like this. So let's take a look a little bit about what's happening there. So this is the tex.web source file, and what I want to do is talk about a box node, right? So boxes are the kind of things that hold elemental representations of lots of things in the tech ecosystem, right? In the tech internal memory representation. They have dimensions, so a box, is holding content that might be of a certain width or depth or height. it needs to link to the content that it's actually holding and things like this, right? And so if we look at, let's find box node size in this file, you'll see that how Knuth arranged this in this massive array of potentially, variable-sized nodes that it needs to hold is in this kind of macro-based format. So there's an explicit kind of global constant that says in the original tex.web, every box needed 7 times as much memory as one of these tokens, right? So 7 total memory words. And the layout of that node is kind of specified in these offsets and these macros that you see here. So the 0th slot in this sequence of 7 memory words is dedicated to holding the so-called node header. And this is something that has information about the link to the next element in a list that you need to know about. That takes up half of the memory word, just like for a token. And then the other half, instead of trying to hold all of the payload of the box node, it's a way of saying, what is the type and potentially subtype of node that I'm talking about here? So the other half of the node header holds, oh, well, this is a box node, and maybe this is a box associated with a horizontal list rather than a vertical list. Right? And then that's in the 0th memory word. What's in the first memory word? Well, you look and you say offset by 1 from the header of the node is going to be this width offset. And so you're going to store something about the width of the box in scaled points, right? The next place holds the depth, then the height. There's something about, okay, the position of the list that the box is containing is stored in this, 5th from the header slot, and so on and so forth. And all of the different nodes that make up the internals of Tex are kind of specified in this way. There's a header for almost all of them. There's a header that has this information about the type and subtype of node and the link to the next node you need to know about, and then some size of additional memory words holding the payload, right? And so, for instance, if we scroll down a little bit, we'll see something about, for instance, insertion nodes. Information here. You can see that their total size is 5, and if you look here, there's a macro that you can use to find something about the 5th memory word, something in the one immediately after the header, and you're just supposed to know that to access stuff in between the first and the last memory word, you should use some of the macros that are defined up above to generically access stuff inside a box. Okay, and similarly, there's something about adjust nodes. We don't even get to know what the internal representation of that is. We just have to kind of go back through the potential set of macros that could access inside this block of 5 memory words. We have to look at how this is called, and so on and so forth. Okay, so let's look a little bit. So I've stored some of the files that I want to pull up. Let's go over to this kind of C representation of the tex.web source code. This is this project from Averson that I mentioned earlier. So part of the question that you have now is you're trying to store, nodes that each take a different total amount of memory in the same giant memory array, right? And you're also storing it along with nodes that are all nodes or tokens that are all exactly 1 memory word long, right? And so how do you do that? You need to kind of build a somewhat complicated function that lets you get nodes of particular sizes, right? So if you're about to kind of build a box node, you need to get a chunk of memory that is long enough, that in the original implementation is 7 memory words long. And you have to kind of figure out, well, what is an efficient way to look through this big total array where each element is 1 memory word long? How do you look through that array for a space which is big enough to hold whatever you're currently looking for? And so this is implemented in this kind of complicated but beautiful kind of like double linked list pattern where there's like a ring of memory and you're kind of keeping track of where holes of different sizes might be, let's say. And this is what this function looks like. You're trying to get a node, you are looping, trying to allocate within different things. You're looking around, you're asking, is there enough space? You keep doing this. You have to occasionally deal with the fact that you want to kind of partition this big array of memory into the space which you reserve just for these single word tokens and the space that you reserve for the variable width token or variable width nodes. And so sometimes you need to reshuffle what the boundary between those things are. And then if there's a problem, as there really often was in the old days, you had to say, well, I've run out of memory, the program ends right here. Program ends here. And so this is like really how Tex memory model works. And this is true of the original Tex. It's true heuristically of all of the current Tex engine successors, PDF Tex, Z Tex, LuaTeX. Actually, I want to pull up the LuaTeX thing so that you can see a little bit more about, well, what is one of these memory words? It's really quite beautiful. And then how do these modern engines store these things? So here is the source file where LuaTeX is defining its representation of a memory word. And the way that they do it, and the way that I'm also doing it, is that each memory word is exactly 64 bits in size, with this kind of interesting property that the way you interpret the individual bits of each memory word might depend on how you are choosing to access it, right? So these memory words, which you can see here, big endian or little endian, might be stored either as something which can hold two 32-bit integers or four 16-bit, half integers or whatever. It might store these things called two halves, which are yet other kind of internal representations of splitting each half in different ways. So for a token, two halves might be what we talked about before, a link to the next token and the payload. For the node headers that form the 0th word of every one of these, almost all of these other nodes, it might be one integer, let's say, that points to the next node, and then a different subdivision of the other half into type and subtype or something like this, right? And so great. So these structures for what is 4 quarters, each of them is 4 16-bit quarter words. 2 halves, those are these kind of unions that could either each be a half word or a half word and 2 quarter words or something like this. And then the memory word is going to be a union of all of these different permutations, right? So you can access a memory word by looking at the glues or 2 integers or 4 quarters or whatever. And there you go. So let's go ahead and look at Vox node size. Oh no, I'm in the wrong file. Let's go ahead and look at how LuaTeX uses this memory word representation, different ways of subdividing 64 bits, depending on how you need it, into different kinds of nodes. So in this file, the tex nodes.h, yes, here's the box node size. And you can see that LuaTeX, maybe I should make this font bigger so that it's easier to read. I apologize for that. Here they've defined a box node as 9 64-bit memory words. I am at least slightly amused by the fact that there is a to-do list item that says make an enumeration out of this. To the developers, I think you can remove that comment. This has been made an enumeration, unless you mean something else. Okay, but then you can see really like exactly the same kind of pattern that was in the tex.web implementation, right? You have these macros that access specific offsets to each of those 0 through 9 memory words. Where, do you want to access the width? You look at an integer in the second slot, or the depth is an integer in the third slot, or the amount of shift and box direction is in 2 pieces of the 5th word, or so on and so forth, right? And I have to say, there's something that I find at least a little bit unaesthetic about this. I don't mean to be too critical. You can see here that this cint macro is a way of looking at the 2 integers representation of a memory word and just grabbing the first one. Okay, and so what you can see here is that in these 3 macros, you are defining an arrangement of the box in which you are putting 32 bits into each slot of consecutive memory words and leaving the other 32 bits of each of those 64-bit memory words completely empty. And on the one level, that's not that big of a penalty. Our computers have massive amounts of RAM, and wasting 32 bits at a time is hardly the end of the world. But I have to say, I find something at least a little bit unaesthetic about this. As I said, I learned a lot about data-oriented design. How does data want to flow through our programs from reading the TeX web source? And in my mind, the way it was supposed to work is something like, you stare into the abyss, and the abyss stares back at you, and then you understand that you should be able to say, the width should occupy, the first 32 bits of one of these memory words, and I should pack the next 32 bits, the depth, into the same memory word, right? There's no reason that this structure has to be 9 words instead of a smaller number or something like that. And so I was always slightly unsatisfied that we weren't able to easily rearrange the internal representation of the memory that forms these boxes. And part of the reason that that's hard, of course, is again this whole macro style accessor pattern that I talked about a little bit in the last video when I was discussing kind of the developer ergonomics of working in these code bases. Okay, so maybe the next thing that I want to do is kind of switch over and say at least a little bit, now that we know, okay, TeX wants to store nodes and tokens in units of these memory words. Usually it's held in one big array, and you want to have ways of kind of packing the payload of each of these nodes into a compressed, compact representation, wasting as few bits as possible. So let me talk a little bit about how I've been working on that. Actually, maybe the first thing that I want to do is go backwards in time. So let's git log one line, and let's dump this just to some random file. I can't even type. That's amusing. Oh, good. It's important that the current commit is about bike shedding. You can tell how I'm spending my time. Let me go reasonably far back in time. Oh yeah, to this one. So this is when, this was from when I first transitioned the internal representation of the giant array of memory from a fixed size array into a potentially dynamically allocating vector. That's something that LuaTeX also did to prevent this out of memory kind of catastrophe from ever happening. So what I'll do is I'll check out that commit, and let me show you a little bit about how this code used to be organized when I was working on it in the early days, how I thought about refactoring it, and then what it kind of looks like now. So the first thing that I want to show is maybe source common. It was in constants, where what I did was basically transition exactly what the tex.web source code was, but just into this code base, right? So you see exactly the same thing. Box nodes are of some specific size, and there's different offsets for accessing the different pieces of information in each of those chunks, right? And what did the kind of memory array look like? So at this stage in the code, I believe I had started tex memory. I'm in the wrong thing. Sorry, tex memory. Find file, right? So what I was working on was to say, the first step is something like encapsulation. And that's not because this is about object-oriented programming. I'm really not necessarily the biggest fan of the object orientation part of OOP, but it's really about, this powerful refactoring idea that, when you take away all of these macros, turn them into, let's say, internal accessor functions of a class, you can kind of keep working on that until you're able to make this vector a private member function instead of a public one. And then at that point, you know that you're safe to start rearranging all of the internals of what goes into this. And you just need to change how it's accessed and how it returns information, right? And so, at the time, this looked exactly like what it looked like in the tex.web source, right? So it's not a macro, but it's a public member function that just returns a reference to, oh, you want to know the width? Look in your array of nodes at some specific width offset, which is a globally defined constant, and try to read off one of these scaled representations of a memory word, right? So this is something where it's like, again, I've got 64 bits, and I'm just going to use 32 of them to hold one 32-bit scaled point integer, basically. And a different 64-bit memory word holds the thing for the depth. Again, wasting and wasting and wasting. Okay. And so, okay, good. So let's say, great, that's what it looked like very early on in the process. And so we can ask, once you're able to kind of encapsulate things and rearrange things, how can you make this more ergonomic, but also more transparent what the arrangement of all of these nodes actually is? Because once you can do that, you can easily start playing around with what the internal representation is. So in nodes, node view, basically I just implemented a facade pattern, right? So I said it's still going to be the case that all of these nodes are going to be stored somewhere in I don't know what, at least this representation doesn't know what. Maybe it's a vector, maybe it's an array. It's going to be held in some contiguous chunk of memory words. And so what I want to do is maybe, first define the idea of, what these node headers are, right? So these node headers have the same kind of pattern over and over again for almost every node type in tex. And so I'll say, well, this thing is just going to hold a pointer to memory words, and then it's going to specify this, okay, part of the node header is about the link to the next node, part of it is about the type and subtype, or maybe there's info, or maybe there's space for extra information because of how I've defined exactly the sizes of all these types. So you can say, okay, so all of my nodes, I'm going to have views onto them, facades onto them, that start almost always with a header. And then I can say, oh, what is a kern node? Something that says, let me put a little bit of extra space there. Well, it's going to be something that, because it inherits from node view, is going to have information about its type and the link to the next node. And then it just needs to store, okay, what is the width of this kern, right? So I'm just going to use the next slot in memory to hold one out of two possible scaled point 32-bit integers, right? And then you can say, well, I can just keep doing that pattern. So there's lots of different nodes that have this notion of width and depth and height. You can see the width and the depth. You can just decide to put both of them into the same memory word and put the height into half of the next memory word. And then let's look at a box. So a box is going to be something that, list box, okay, it's fine. So I have something specific for boxes that take, okay, it now has a header because it's a node view, and a width, depth, height because it has dimensions. And then it also is putting information into another memory word. And then a box node will be something that, because it inherits from those, has access to width, depth, height, and stuff about the list pointer and things like this. And then also whatever else the box needs. And because we've controlled exactly what the internal representation is, we can do things like, earlier, height was stored in the first slot of the word offset by 2 from the header. And so I can say, oh, let me, make use of the fact that I know that there's 32 bits of empty space and use that to store a different part of the payload of a box node, in this case, the shift amount. And so here you can see I've been able to kind of pack the original 7-word 32-bit representation into 4 64-bit memory word representation, which is, exactly the right mathematics, right? And this is the kind of thing where if you want to change, if I would decide to add extra information here, like related to sync tech functionality, I can just change this size to 5 or 6, I suppose, and then, add accessors here that say, here's how to interpret, here's how to access what's going to be in that extra slot, and it will just work, right? It will just work, which is kind of nice. The way that that's all set up is kind of because I completely changed the way that tech memory representation looks. So let's tech memory. So here, I've been able to transition from a single monolithic vector of memory words to a group of separated memory pools that are each of a fixed size, right? And so you can see basically what I have here is an array of vectors that store memory words with kind of information about how many nodes are used up in each of these and where do they start in memory and things like that. And in part, one of the reasons to do that is that now there's no piece of memory that needs to hold, nodes of variable sizes. And so if I go to the get node representation, you'll remember that earlier, let's see, tech, C code, what is this under? It's under data structures and memory, get node. Get node was this, long, complicated function because it needed to know not only how to kind of shift the boundary between the fixed size portion and the variable size portion, but it needed to know when it was working with the variable size portion, how do I find chunks of space of the correct size in an efficient way? And now, actually, that's trivial because I have a separate block of memory for nodes of different sizes, And so finding the next, piece of available memory is as simple as keeping track of, well, what is the next available slot? And if I release some memory, just say the next available slot is that one. And so this kind of process of getting and freeing nodes that used to live as variable sized entities in this monolithic array is now much, much easier, right? And you might wonder, how do you appropriately index into the right pool? How do you know for a given, link to the next node, how are you supposed to know which pool it's even going to live in? That's maybe something that I'll talk about a little bit more in the next video when I talk more about how do we use this kind of restructuring of the underlying memory in order to kind of allow tech to run faster with the way that modern hardware wants to interface with, the cache and your memory and things like this. Okay, so I hope that was at least a little bit interesting. This was a little bit more of a background on tech than something specific to this tech engine, but I hope it was interesting. And until next time.